I'd like to introduce our speaker for today, John Wolosik. Many of you are likely aware of John as he is well known throughout the industry for both his engineering and construction achievements, as well as his giving back to the profession through his active involvement in professional societies. John has more than 40 years of experience in geotechnical engineering and contracting, and I've been fortunate to work with John for the last 25 years at Keller. He holds a BS and MS degrees in civil engineering from the University of Illinois at Urbana-Champaign and has authored more than 35 papers. John has been the recipient of many awards, including the 2008 National ASCE Geo Institute Martin S. Cap Award and Foundation Engineering Award, and he was named the Georgia Society of Professional Engineers Engineer of the Year in 2017. John is also the past president of the Deep Foundations Institute. I will now turn over the session to John for his presentation on slope instability and repair. Take it away, John.
Thank you, JD. I want to tell everyone thank you for joining us this afternoon. I think this is going to be a lot of fun. It's one of my favorite topics. And to start off with, we'll talk about some learning objectives. They are, what are the primary causes of slope instability? What methods are available to repair slopes when they fail? And this is what we'll talk about mainly, all of the available methods offered by geotechnical contractors for slope repair. And then cost is a big item, obviously, on every project that we do. If somebody tells you cost is not a concern, they're lying. It's always a concern. So we'll look at what the costs are for all these methods, which are the least and most expensive, and the reasons why. To start off with, though, here is our agenda. We're going to have a quick safety moment. I'll talk about our company a little bit, and then we'll get into the meat of the presentation and talk about a few case histories, followed by a summary. So for a safety moment, the first thing we want to mention is the crazy year that we've all experienced with the COVID-19 and how our company has reacted and implemented a lot of different control plans. And we've been very fortunate through this whole thing and been able to keep working as a construction company, which is seen to be an essential business. So we've done all of the things that people typically are doing in larger businesses, and we're coming through it, and hopefully we've got better times to come. What about Keller? So Keller is a multinational company based out of London, England. They purchased our old company, Hayward Baker, back in 1984. Keller is active in 40 plus countries with over 190 offices. And I'm one of more than 10,000 people that work at Keller. We do a lot of work, more than 7,000 projects a year, which is incredible when you think about it. And one of our catch lines is we have a local understanding backed by global strength. Here in North America, Keller has offices all throughout the United States, shown by these little dots here. Each one is sort of an entrepreneurial group that focuses on their local regions. They offer all our products, and we're all interconnected here in the States and across the globe. Okay, so every day, people live and work and play on ground that we've prepared on many different projects, many energy projects, hospitals, stadiums, etc. So we work across the entire construction sector. So let's talk about our topic for today, slope instability and design and repair of slopes. So what are the major causes of slope instability that we see in all projects, and particularly that affect roadways and embankments? Well, we have to say that it's water, okay? That is the primary cause of slope failures. Rain, water, moisture, H2O, whatever you want to call it. When water gets involved with the soil, things happen. Where does that water come from? Well, it comes from snow melt, heavy thunderstorms, tropical storms, And what does it do? It causes the soils to weigh more. They're heavier. We get groundwater table rise, which floats the soil and can make it lighter at the toe, which can hurt your slope as well. Erosion, lots of erosion occurs in these big storms occur and can cause scour in streams. It can tear up your fill slopes, etc. Rapid stream flow will contribute obviously to that scour. And then the worst slope instability that we have is rapid drawdown, where you have the heavy soils and yet the water table is very high, and you have your least factor of safety during the rapid drawdown condition. This is a project we did many years ago in west central Wyoming for the Wyoming DOT called the Blue Trail Slide. It was located in the Snake River Canyon, and every year when the snow melted, they had tremendous floods, as you can imagine, in the Rocky Mountains there. And this is just a helicopter view on the left of the slide repair. We found over 20 feet of asphalt on this road. It had been repaired so many times since the late 1950s. And on the right here, you can see some evidence of the scour that occurs or occurred at the bottom of the slope. So every year it flooded, it cut the toe of the slope, and it moved a little bit, or a couple of feet in some cases. So we repaired this slide, I believe, back in 1997. So the computer is acting a little slow here. I apologize. So what are some other instability causes in slopes? Well, it could be adverse geological bedding. If the beds are dipping into your slope and you cut into it, for example, you're going to have gravity acting against you if there's sliding along the beds. That also can happen, of course, when you have soft place seams in the bedrock, which is a pretty common condition in a lot of different geologies. Sometimes it's an over steep cut or fill slope where construction has occurred and they've cut the slope steeper than 1.5 to 1, or they fill the slope with less than a 2 to 1 slope. Excuse me. Also, when fills are placed on slopes and no benching has occurred in the existing slope, you can oftentimes have that fill just slide down the old geometry and that benching hasn't occurred. We see a lot of inadequately compacted or non-engineered fill soils. They're either dump sites, old fills from old mining. They could be very old, etc. But anytime there wasn't an engineered design and construction where compaction was done appropriately. Another reason or another cause is adjacent construction. Either a surcharge is added at the top of the slope, either a fill embankment or a building in some cases, or maybe the toe of the slope is cut. If it's over the property line, for example, somebody could come along and cut the toe of that slope and cause instability. Vegetation is our friend in slope stability. So if you have a lack of vegetation, either on a newly constructed slope that's so steep that you can't grow on it, you've got the wrong type of plants, sometimes clear cutting is involved. We did a large landslide project in Maryland one time when someone wanted a better view of the Chesapeake Bay. They cut down all of the trees so from their building they could see the bay, but unfortunately by taking out all those trees they caused a huge landslide. So but any kind of land disturbance is going to let the water get in there and cause a problem. So let's talk a little bit about design. This is not a design-centric presentation, but I think we should mention a few of these things just to get a proper discussion going here. So commonly when slope instability problems are addressed, the design that's used these days is a software. It's the most common. When I started doing this 40 years ago, we did it by hand. I remember getting a TI 55 calculator that was programmable, and that helped me do the calculations more quickly, but obviously nothing like we have today. So it's typically these slope problems are designed using software that uses a limit equilibrium theory. So finite element analysis can also be used, but it's typically used much less frequently in slope stability. It's still used by some folks, particularly in real high profile projects, et cetera. But there are so many input parameters involved that it's much more sensitive to the answers, to the soil parameters and the answers you get. So typically people use limit equilibrium. You should use good site mapping whenever you're looking at a slope problem. You need to go out and look at it. Geologists can be really helpful in that area, along with geotechnical engineers, to identify scarps, bulges in the ground. You can look at topographic maps and run sections, obviously, and then having inclinometer data to help define the slide geometry, the depth of the slope, is just invaluable. So drilled inclinometers with a series of measurements. I caution you to be careful with computer analysis. You know, don't just believe the numbers without looking at it and making sure that it makes sense. There could be silly mistakes made that are that need to be checked, and don't believe everything your computer says. Make sure that it's a sensible answer. One thing that I've noticed through the years about design is that sometimes due to adjacent property lines, et cetera, but people use very steeply dipping soil nails or tieback anchors. Sometimes the limit equilibrium software isn't able to handle that calculation very well. So be very cautious whenever you use steeply dipping anchors or nails, and also if you're looking at a very steeply dipping failure surface. It causes an intersection between the nail and the failure surface that can be geometrically very difficult to calculate. And many softwares do not tell you if they have non-convergent failure surfaces. So if it doesn't converge, they just give you the lowest factor of safety answer that they were able to calculate. It may not be the lowest number. And so if your software doesn't do that, you should ask your provider why that is, or if they could provide that to you, because sometimes those non-converging surfaces can be the ones that are the most important. I have a problem with my computer here. It makes me punch it a couple times before it does it. I'm sorry, I'm not sure why. So what kind of information do we need for this design? Well, number one, we need a really good geotechnical consultant to go out and get us some good borings or CPT data with rock cores as needed if that is involved in your particular problem. We need to know where the water table is. Inclinometer readings are invaluable. But basically what we need is really good representative soil parameters and good lab testing. And all the things I've listed here. But one thing about a slope failure that you should really understand is it's a really good test. It's failed. So we should be able to back calculate soil parameters if you know the slide geometry, the groundwater level, et cetera. So it's already failed, and it can tell you exactly what the soil parameters are if you use back calculation. So I want to point out that design build contractors like Keller do this type of thing every day. It's a regular part of our work, and so we offer this as a design build service to repair slopes, and we're very familiar with the design and the construction. And unlike someone that maybe does one a year or two a year or something like that, we really can get down to the best solution very quickly. This is just an example of a slope inclinometer reading. A slope indicator is a plastic tube with slots in it. Then you send a probe down, and it can measure thousands of a millimeter. It's incredible. So these are results taken way back in 2005, 2006. And you can see as the calendar moves along how this slope failure is progressing. So it's up to about 1.75 inch movement, damages occurring, et cetera. This is the A and the B axis, either parallel or perpendicular to the slope. And we're able to assess that there's a slope failure somewhere down around the 460 elevation to 465 elevation here. And that way we know the geometry of our slope so we can start our calculation. So global factor of safety is a typical measure of repairing a slope and looking at a slope in general. And so that global factor of safety is defined as the ratio of the resisting to the driving forces. And so there's a typo there, I apologize, but what we're trying to do here is add resisting forces with our repair. And so in doing that, we'll increase the factor of safety. Oftentimes, factor of safety of 1.3 to 1.5 are used, but it depends on the situation. And if you want a good discussion of that, I reference this paper I wrote back in 2010. It's from an ASCE conference that was held in Seattle. Conference number 3 that you see here is a big, thick book. If you don't have it on your shelf or in your digital library, I recommend it highly. It's a great book. And it talks about the stabilization of 7 different large landslides all across the United States. So this is what the software results look like. This is nice. It's a graphical format. In this case, we're looking at a soil nailing problem adjacent to a building with a creek down below or a high water table. And so in this case, what we're doing is we're drilling in soil nails, the number 8 bars on 5-foot centers, 20 feet long, 4 rows. And the yellow material is a fill material where this building has been built on a significant fill. But in this case, we have the common problem of the floating toe, where the groundwater table is affecting the resisting forces down at the bottom of the project, and is very common in our what we look at. So this is a design software output for soil nailing. Here's one using soldier piles and tieback anchors in a thick colluvial deposit. Colluvium is a detritus material that has fallen downhill along the side of a hill or a mountain for millions of years or thousands of years. And you can see here a little dot, which is the center of the circle, the red dot that shows the global factor of safety of 1.43. But here we're applying these horizontal forces via tieback anchors to a soldier pile, giving us 5.5 kips per foot. So typical output. And here's one you can see with also a fill slope with a building adjacent to it, where we're using a technique called soil screws. Soil screws are helical anchors that have helices all along the anchor, not just at the very end like they do in helical tiebacks or helical piles. And you can use this type of software to design soil screws as well. So let's talk about some of the repair methods and just talk about some ballpark costs as well on what we can do to repair slopes. So here's a long list of different methods and just some qualitative costs with dollar signs shown here. The most common method for stabilizing slopes is just the earthen berm. I talk about this in that paper I referenced a few slides ago. Berms are very effective. Everybody knows how to do grading. You can calculate it easily, but I caution you when using a berm to make sure that you understand all of the geometry of your slide. I've seen so many berms that have been placed that actually decrease the factor of safety of the slope. In fact, 4 of the 7 case history projects that I mentioned in that paper, they'd already used berms before we had to go in and fix it with drilled and grouted elements. And so they're effectively, they doubled the cost of this project and caused a lot of heartache and lawsuits, etc. So use your earthen berms, but make sure that you look at the downhill geometry. Just because your owner only owns to a certain line doesn't mean that the slope doesn't continue on for another half of it. So be careful with earthen berms, but obviously they're a low cost solution. Horizontal drains are great. There's nothing, or they're a very inexpensive solution. There are a lot of good contractors that install these. You go in and you can decrease the water table, which makes a tremendous difference in drainage in your slope stability. I just caution you that they can be clogged with silts if they're not installed and filtered properly. And then in warm weather climates like we have here in Georgia, where I am, typically they only last for about 2 years before they get clogged with bacteria, these anaerobic bacteria, microbes, etc. And it's very expensive. Most people don't maintain them. They don't go back out and maintain them, and you have to flush some pretty nasty chemicals in that you later have to collect and dispose of when you're trying to flush horizontal drains. So particularly they work great in Canada, Minnesota, northern climes where you don't have as many bugs like we do here in the south. So horizontal drains are great. I love soil nailing and rock bolting. I've been doing soil nailing since about the mid 80s, and it is a fairly low cost to middle cost solution depending on what type of casing that you use. I'll talk a lot about soil nailing as we move along. Sheet piling is something that's come back in a major way in the last few years because of these new modern track-driven machines that can vibrate or press sheet piles in place. You don't have to immobilize a big crane, pile driving hammer, etc. And so sheet piling can be a medium cost solution and one we use frequently. It gets a little more expensive, obviously, if the wall gets taller and you have to add tie-back anchors. We use a lot of tie-back anchored concrete reaction blocks. This is a medium cost solution. It's really environmentally friendly because you can bury the block when you're done. You don't see a wall there. They're great because they eliminate the need of a soldier pile, which would be expensive. So you lay these reinforced concrete blocks in the ground, drill an anchor through them, and the big blocks then transfer the force of the tie-back anchor to the slide and stabilize the slide. I'll show you some case history about that coming up. Soldier piles and lagging can be used either non-anchored or with tie-back anchors. They're a great solution, particularly in the non-anchored, for a lower cost in the non-anchored solution. I'll show you that as we move along here. Obviously, the cost goes up with tie-back anchors, but you also get a lot more capability and resistance by adding that. And then micropiles can be drilled into the earth and intersect field planes and act like dowels and resist the slide in failure. And we'll talk a little bit about that. And then there are various aesthetic treatments to make these systems look better that typically add to the cost on top of all this and can get to be pretty expensive. It can also be very beautiful. So let's talk a little bit about sheet piles. As I mentioned, it's a mid-cost to high cost, depending on whether or not you need tie-back anchors. Also, if I can get my little thing to work here. So this is one of the modern machines that I mentioned. It's a very fast solution. There's no drilling. You just press it in with these modern hydraulic machines. They can be vibrated, drilled, pressed. Without anchors, it's a passive system. It doesn't work in boulders. Obviously, if you're trying to press these sheets in the ground and you hit a boulder, it's going to stop. You can do pre-drilling in that case, but that adds to the cost, obviously. And so A couple of cool things about sheet piles is they can be used, reused. You can use them on one job as a temporary solution, pull them, use them somewhere else. Different companies will actually rent you the sheet piles. If you don't mess them up, they'll let you use them, pull them back out, and bring them back to them on a rental basis. So that's kind of cool. There are basically a couple different types of sheet piles, both hot rolled and cold formed. The hot rolled sheets are often called Z sheets. They're shown here on the left and in the diagram in the middle. That's a typical PZ sheet. Uh, they're identified typically by the weight of the sheet per square foot. And so they're hot rolled. They have a interlocking connector that's rolled in and it's pretty robust. They're more expensive than the cold form. The cold forms don't have the same capacity. They're a bit weaker, but they're just basically cold formed or bent in place and thinner, but much less expensive. So both are used in many different. This is the modern drill or sheet pile installation machine that I mentioned here, sheet pile driver on the left, which is a hydraulic machine with a fixed mast. You can put some short sheet sections that are shown in the foreground there and press or drive these in using that machine. And to the right here, you see the more typical that we've known for many years, a big crane with a hanging vibratory sheet pile driving machine like an ape or something like that, that is able to shake these machines in very rapidly. So both work well. This is just an example on a project in Vicksburg, Mississippi. There was a big landslide and they had to run the traffic on one side over about a 6-month period. And so the slide was actually coming all the way across the median. You can see on the right and on the left, the grassy area, that's the median between the lanes. And where the scarp was cutting across, they installed sheet piles, and it worked very well to stop that intrusion of the slide across the lane. So another solution down the list here, one of my absolute favorites. This is a mid-cost solution, and tie-back anchored concrete reaction block. So in this case, the cost is a little bit less because you don't have to pay for a soldier pile, or sheet pile, etc. These reinforced concrete blocks can be precast and hauled to the site. They can be cast and placed on the site or shotcreted in place. You have to have access to benches at each level that you're going to install your anchors on. But it works in all profiles. It's active, meaning it, we actively stress the anchors and push these blocks down to the earth to provide resistance for the landslide forces. But when you're done, you can cover them up. You can plant grass or whatever you want over, and they're not seen. So typically these slopes are revegetated. This is a pretty environmentally friendly solution. This is just a view of that same project in Vicksburg, Mississippi. We actually used the lanes that they closed, built our formwork, and then just brought in concrete trucks, excuse me, and put in the reinforcement, and we cast blocks ourselves. You can see the steps here. That was done to try to save weight on the blocks. But then we're able to pick them up with a hoe and then carry them down to the site. Excuse me a second. So there were 5 rows of these anchors. This was a massive landslide. I believe it was about 40 acres that were sliding. And here you see the upper row and actually a couple of different drill rigs here drilling deep tieback anchors. These anchors were as deep as 275 feet. Incredible landslide. And this just shows the use of those tieback anchored reaction blocks. This is another project that was done just south of Nashville, Tennessee, where the blocks were applied equally well. These blocks are a little bit smaller. The forces were a little smaller, but once again, a pretty significant landslide. So soldier piles and lagging are a solution where you can put soldier piles in the ground. They're either driven, pressed, or drilled in place, drilled and dropped, and they're put on about 8-foot centers or so, as you see here in the animation. And then we start digging down and we put in some type of lagging. It can be wood for temporary, steel, precast concrete. You can shotcrete it in place. And this is a very popular solution. I'm sure you've seen it in a lot of different places. It could do about 10, 12, maybe 14 feet tall, something like that. It's a good solution in urban areas because you don't need any right of way behind the wall for like a drilled anchor, etc. So this is a really good solution to use in many different cases. And so we can either drive those soldier piles, as shown on the left here, with a pile driving hammer. This could be a hydraulic hammer, which is shown here. Obviously, the old diesel hammers are still used. You don't get the same precision with the location, particularly if you've got some kind of obstructions, etc., in the way, but we use this a lot. And then on the right, you see here the drilled, dropped, and concreted solution, where we have a drill rig. We drill a hole using a caisson type drill. We then can carefully place or drop the beam and brace it in place, and then pour a lean mixed concrete that can be shipped out in between. So very, very popular solution as well. Different types of lagging include wood lagging, which you see here on the left. It can be treated and used as a permanent solution. I've got some projects that were done in the early 80s with treated lagging that are still serving very well. On the right here, this shows a shotcreted lagging. I show this slide on purpose because these soldier piles were driven and there were some obstructions in the ground here, and you can see it's kind of wonky looking. We talked about this with the owner, and they liked the lower cost solution, obviously, drive rather than drill. And so you can see here that when they've hit certain obstructions, they can pitch in, they can pitch out, they can pitch left to right, etc. So keep that in mind. And then we can use the soldier pile and lagging solution with tieback anchors. As the wall gets taller and the loads get higher, this is a relatively high cost, but absolutely proven system that changes the passive cantilever system into an active anchored system. So oftentimes, most times, these are obviously steel piles. They can be made out of reinforced concrete, like a drilled shaft. And many times these days, we use micropiles as a soldier pile. So that's a nice solution that can be bring the cost down. So these are typically either temporary or permanent drilled tieback anchors. The permanent ones have double corrosion protection, and they're all semi or pressure grouted, and it works in all soil and rock profiles, and there are many different facing options available when you do this. This is a project from Lexington, Kentucky, where a mechanically stabilized earth wall had failed, and this is for the Walmart folks, and we put this very nice looking double anchored wall in front of the failed MSE wall and used some very attractive precast concrete blocks. This was not cheap, but it's a very nice looking wall, as you can see here, and it's one of the lagging types that are available when you're using soldier piles and concrete. The tiebacks themselves, the drilled anchors, can either be bars or strand. Typically, we use, excuse me, like a grade 150 pre-stressing steel bar, all thread. They're available in some very large sizes these days. Typically, the larger sizes are used more for micropiles than for anchors because they're so heavy, placed down an angled hole. Strands are used very commonly. It's a very high strength pre-stressing strand that you see here, and they can accommodate any load that you want pretty much, and are prefabricated by our suppliers in certain lengths, and we are able to place them all in one piece down the hole. The grout that's used to secure these tieback anchors into the ground is a cement grout with a very low water cement ratio of 0.45. And then there's an anchor head, bearing plate, and a trumpet, which is a pipe that helps us with protection. Shown on this drawing here, there's an upper unbonded length that has typically a greased and sheathed section that allows us to stress the anchor actively. The lower section is bare strand or bar, and it's all grouted in place, and we test every anchor. This illustration is from the FHWA Geotechnical Circular number 4. If you don't have it, it's available downloaded from the FHWA website. So the cross sections of those anchors are different between the unbonded and the bonded zone, obviously. We have centralizers that are involved. There's drill hole. The strands are greased and sheathed in the unbonded zone, as shown here. They're wrapped in grease and a plastic sheath, and they're bare steel in the lower zone, but it's all encapsulated for a permanent anchor in a corrugated plastic tubing that provides corrosion protection. This is a project from Shreveport, Louisiana, that was done as a repair for the Louisiana Department of Transportation and Development. It was a very interesting case history where a reinforced earth wall that was pretty old had been sitting there for a long time, but unfortunately it was so flat that there was really no drainage going on. So decades after it had been in service, because the water sat there without draining away, it softened the clay on the surface, and this wall slid about 25 feet, actually slid across the property line into a private property. So incredible project. We came in with a soldier pile and treated wood lagging system, and were able to stop that wall in its tracks and repair. It was backfilled behind, and it was along Interstate 49 right in. So when we use soldier piles, like are shown in this previous slide here, how do we get the anchor through that beam? I get that question a lot. So this is a through beam anchor pocket. We actually cut a couple of holes in the flange of the beam. We cut out the web, but then we weld in this box structure shown on the right here. So we replace that material for the web. We also weld some plates on the flanges on the front and back to replace the steel we've removed here. So that enables us to put these tieback anchors right through the soldier piles. Works very well. Here you see that in place, and we're actually physically stressing. We're pulling on the tieback anchor, the strand anchor, using a hydraulic jack. Every one is tested to make sure that it meets the specifications. So we pull on it. It's Hooke's law. It's delta equals PL over AE, and we check that. Test the anchor typically to 133 to 150% of their design load, and then take them back and lock them off, typically at somewhere around design. So every anchor, every tieback anchor is tested. This is just a close-up view of that through the beam anchor with the bearing plate and anchor head. You can see the wedges here that grip the strands. Soil nailing. Soil nailing is one of my favorite applications. As I mentioned, I've been doing it since the mid to late 80s. So it's a top-down technique. It's a low-cost solution where you basically dig down about 5 feet at a time. And the tallest soil nail wall I've done, I think, is 74 feet tall. That's really tall in Active, Mississippi. But you just keep on going. You dig down, you install the soil nails, which are typically about as long as the cut is tall. And so if you've got a 20-foot cut, you've got a 20-foot nail, something like that. And then the facing is applied as you move down in 5-foot increments. It's typically a reinforced shotcrete, but it can be a lot of other things too, we'll talk about here. One of the things you have to have is stand-up time. The soil has to be able to stand on its own for that 5-foot cut. If you don't have that, for example, if you're in Florida and you've got clean sugar sands, it's really hard without pre-grouting. You dig down 5 feet and it'll just run out on you. So you need that stand-up time. It works really well in a lot of different regional soil profiles. It's very versatile because you can just keep on going when you hit bedrock. Turn it over into rock bolting. It's a passive system. We don't stress these nails like we do in tieback anchors. We let the movement of the soil and gravity cause the tension in the nail. So it moves a little bit more. You're going to get a little bit more movement with soil nailing than you would with a tieback anchor solution. So you can have problems in urban areas due to high utilities. That top nail has to be installed about 2.5 feet down. So if you've got utility trenches, that's a real problem. And if it's a soft, unconsolidated fill in the upper zone, soil nailing doesn't work super well in bad fills either. So there are a lot of different facing and finishing options, though, and I'll talk about those as we move along. To understand the concept of soil nailing and as it's done in a top-down manner, number one, and number two is how does it work? This is a little illustration we put together. So these are theoretical Rankine failure planes that are on phi minus 45 over 2 and phi plus 45 over 2. And so they intersect, and all these failure planes are possible in a soil nail application. So you can see here that the nails cross across, they're drilled and grouted right across all of those failure planes, and they support the soil across those failure planes, which is really great, as you can see here. So what we're actually doing is we're creating like a reinforced block of soil that actually also works as a gravity wall. So it works really well. However, the nails don't cover these little triangles at the face. And so we need our facing, which is some type of shotcrete or steel mesh or something, to restrain those soils at the face. So that's sort of how soil nailing works, and it's a really great technique. And it's about 20% lower in cost than the tieback anchor wall. So as I mentioned, economical. This is an illustration that's very interesting out of the FHWA Geotechnical Circular number 9 on soil nailing. And it shows how in the top down, when you excavate 5 feet at a time on phase 1, 2, 3, 4, etc., that you're installing the nails. And so these are the theoretical failure planes you see here for the top row, the second row, the third row, etc. And so these nails are acting differently every time and providing different support every time you dig down. By the time you get to the bottom, the top nail is doing very little, but it's done a lot for you as you've excavated down. So that's something that has to be looked at in soil nailing. It's a little complication, but it's a great technique. I love it. And so as that nail is working, what it's doing is it's fully bonded, unlike a tieback anchor. And so wherever that failure plane is and it's moving as you're building it, you get resistance on the backside of that failure plane from the nail in pull out, but you're also connected because you're fully grouted to that failable block on the left side of the failure plane. And so it's giving you stability in that way, in that manner. So it's good for a lot of different excavation support options or projects, roadway widening, infill removal, and of course slope stabilization that we're talking about today. For the soil nail materials themselves, we use all thread bars, but they're typically lower strength bars than those big grade 150 pre-stressing bars that we use in tiebacks. They're grade 60, 75, some are 90, 95, 100, etc., offered by different manufacturers. They're all thread, so you can put a nut on the end. Excuse me. We use a epoxy coating on the walls when they're permanent. You can also use what's called hollow bars. They're a bar that's drilled in place while you're pumping grout through the middle of the hollow bar. I'll show you a photo of those here in a moment. They're great for soil nailing. Or soil screws, which are the helical anchors that I mentioned with closely spaced helices up and down the bar and shown on the illustration here on the right. And so we use the same cement grout here, the low water cement ratio grout in soil nails that we do in tieback anchors. This is an illustration of a project in Greenville, South Carolina, where we're using hollow bars. You can see they're stacked up on the side here. We're flushing them in with a stay in place sacrificial bit, and we flush the grout through the bar and through the hollow middle, and it flushes out around, cleans the hole, and then it's just left in place. Very common these days. We do sacrificial soil nail pull-out tests. We do not test every nail like we do on a tieback anchor. So it's typically one nail per row that we'll do a pull-out test on. We'll actually install a sacrificial nail and we'll attempt to pull it out. This is just an illustration, or excuse me, a photograph that shows all of the components. A block that we set against the wall, we pull on it, we measure the deflection. Here's the hydraulic ram, and we measure the load. So to confirm our assumptions on the bond stress for the soil nail. There's a project in Colorado where they've removed the infill at a bridge so they can add a lane at that location, actually widen the road without having to do a big revision on the bridge. So this is soil nailing here on the right with what we call a rough gun finish. This will get a cast in place concrete finish in the end, which is pretty common in DOT projects. For temporary excavation, or if the owner wants to save a little bit of money, we can do what we call the permanent bump finish, where we actually just thicken the shotcrete around the nail head for the soil nail to provide corrosion protection. You see here, it's kind of funny looking, the pimple wall. And here you also see at the bottom some weep holes that are connected up to chimney drains that have been placed against the soil and shotcreted against. Very always required in soil nailing, as well as a construction joint or a tension joint that you see here in the middle. Here you see a finished shotcrete. On the left is a cast in place wall that was built on a project. We soil nailed right up to it from the right, and we're able to screed that wall and use concrete finishing techniques to give a smoother wall than that rough bump finish I showed you before. We can get fancy. This is expensive, and we can stamp these walls and stain them. This is a project for the Atlanta Falcons NFL team. They wanted a nice looking wall. This is soil nailing, and we stamped and stained it. Or we can do a sculpted finish and make it look like a rock outcrop by sculpting the wall, carving it, and we can also stain these to look very nice. We have many of these projects across the country. Here's a project that we used a wire mesh facing, echo mesh, supported by soil nails for a landslide project in Toccoa, Georgia. It was a slope failure, and there was also an intermediate road down halfway down the slope, and we were able to support that mesh with the soil nails and then plant vegetation and allow it to grow through. This is a very nice solution of many projects. So as far as cost goes, in an analysis between soldier piles and tieback walls and soil nail walls, you see that these are the different things that you have to consider. Soil nailing is typically cheaper as long as you don't put a real expensive facing on there. It's also very quick. They're both top-down techniques. One is a passive technique and the other is an active technique. Soil nailing has a few limitations: soft fills, soft clays, etc. It doesn't work very well. or in urban areas. So obviously you get more bang for the buck in many cases with the soldier pile tieback wall, but you're going to pay more for it. So they both work very well. So let's just talk for a second about micropile walls. This is a solution that's been around for about 30 years or so. You can actually drill micropiles into a landslide with little or no excavation. It works in a lot of different profiles, often used when you have soil sliding on bedrock. It's typically a passive system, but you can actually add tieback anchors to this as well. In my experience, it only works for slides less than about 25 feet deep. When you add tiebacks, you can go to 30 to 35 feet, but it gets a lot more expensive. So just like the anchored block solution is very environmentally friendly, it can be buried and invisible. So this is a project that we did in Milltown, Montana, for an interstate where they were transforming this lake and removing the dam, which had some contamination in it from gold mining from the 1800s. They were actually going to remove the lake, and you see them taking out the sediments in the upper part here. And so when they removed the lake, they were then going to expose this bridge, which was built after the lake, to the ups and downs of the river of Milltown Creek, which could cause instability due to rapid drawdown. So in plan view here, what we did was we went below the bridges, and what you see here is a reinforced concrete micropile cap, and then individual micropiles with alternating batters were installed as shown here. So in a section view, you see here the alternating batters down to bedrock. And on the right here, we drilled a steel pipe in, a steel casing down to bedrock, but then we drilled a socket through that and grouted a bar, an all-thread bar through that socket. So here you see the drilling going on alongside the river under the bridge in not terrible low headroom, but limited headroom. And then once the piles were in place, you can see the guys cutting them off and preparing them, and then placing formwork to cast the cap. That cap acts as a connection between the piles because you're going to have compression on the downhill pile and tension on the uphill pile. So it gives you sort of an A-frame effect to hold the landslide in place, the slope instability. So let's just look here in the last couple minutes of a few short case histories of slope stabilization. This is a project from Leesburg, Alabama, where after a big hurricane flood, there was tremendous erosion and the fill slope failed, as you can see in the upper right here. That was repaired using soil nailing with techo mesh, vegetative planting in the techo mesh. You can see the soil nails and the mesh on the left. This is before the plants had taken hold. And then gabion wall at the top, which is a rock-filled basket to reestablish the shoulder that's been lost. This is a pretty project in Vicksburg, Mississippi, done for the Mississippi River Commission, where in Luesio silts, they'd had slides between these bridge piers. And so we were able to come in and use soil nailing with shotcreting and put in two different walls, both above and below this bridge pier here, and do a very pretty solution that provided stability and also good drainage with a rock channel on the right there, left, excuse me, of the right photo. So this worked out very nicely using soil nailing. Here's one in Gatlinburg, Tennessee, where we went from clay to bedrock, and it was an erosion problem basically, and so we were able to come in and use both soil nailing and rock drilling and rock bolting, and then put on a shotcrete facing to stabilize this slope. And here's one just to the east of Louisville in Prospect, Kentucky, where a very upscale community wanted a marina that led through the woods onto the Ohio River. So they dug this big marina out at the base of the slope below their condominiums. And unfortunately, they undermined their slope and caused a slope failure that was a big problem for the uphill buildings, as you can imagine. So we came in with the reinforced concrete. These were precast and delivered on site, and drilled in deep tieback anchors that were later buried and couldn't be seen anymore. Okay, so those, we're coming near the end here. We're trying to answer a few questions. We're a little long on time, maybe a couple minutes, but those are the different options and some case histories for slope instability. So, JD?
Yep. I'll thank you, John. As always, an enjoyable and informative discussion. We are a little bit long on time, so what I'll do is I'll pick one or two questions that we'll look at, and then we will follow up. We've copied all the questions. We'll get them to you, John, and we can get them back to everybody by email. Now, as a reminder, we have 1 hour of PDH credit available for the session, so please respond to the poll that you see on your screen to register for the credit. If you do that, please. These aren't in order, these questions. I picked a couple of them that I thought might be interesting to hear since we only have a little bit of time here. The first one is, throughout your rich years of experience, which project related to slope stabilization was the most challenging and why?
Wow. I think there were probably two, one of which was shown on here. And they were done quite a long time ago. The first one was the Blue Trail slide for the Wyoming Department of Transportation near Alpine, Wyoming. It was just such a massive landslide, and the forces involved were incredible. And unfortunately, while we were designing it, code changed, and they basically quadrupled the seismic load on our system. And so it was a real challenge to accommodate that change in loading and to get it done. And fortunately, the Wyoming DOT was such an excellent partner working in the design build arena that we were able to do it and pull it off. About 20 years after that slide was done, there was a debris flow that started about 1,000 feet above that slide that slid into the river and temporarily blocked the river that was only a couple hundred feet from our slide repair. So that was quite a challenging day, as you can imagine, or days when that happened. And then the second one would be that 74-foot high soil nail wall in Natchez, Mississippi, that was done for the U.S. Army Corps of Engineers, Vicksburg District, and local Vidalia office. So it was, once again, a design build project. Something like that hadn't been done before. We built an MSE wall with lightweight backfill, et cetera. So those are the two. And just because things like that hadn't really been done before.
Yeah. Interesting. And one more, and then we'll let everybody go here. What are the safety challenges of working on unstable slopes?
So I talk about this in that paper I referenced in the ASCE from 2010. There are many challenges. The thing is that the slope is failing, and so if during your pre-project planning you can do some proactive work like excavations, trying to decrease by digging uphill the driving forces, plan your operations so that they're safe, where you're operating from the areas where the slope is the most stable to the least stable. And every day try to leave the slope better than it was the day before. But it is a real challenge. It's something that requires a lot of experience and forethought, and it's just a challenge to work on a slope that's actively failing while you're there. We did one in Chattanooga, Tennessee, on Lookout Mountain about 6 or 8 years ago. The darn thing had mud flowing all around us, and so we had a couple of really good guys on dozers who were managing that and keeping it from hurting our operation or causing safety concerns. So it's a real challenge. It's something that takes a lot of experience.
Good deal. Okay, well, we've gone about 5 minutes past, so we'll go ahead and sign off now. But thanks again, John. As always, a great presentation. You can contact John directly at his email address is jrwolosick, WOLOSICK at keller-na.com, or through LinkedIn. Or you can just go ahead and reply to this invitation and we'll get your message over to John. Thank you for attending.
I put the email up on the screen there, Jay.
Great, excellent, excellent. And I'd like to thank everybody for attending, and I hope you enjoy and benefit from today's webinar. Stay safe. Thank you, everyone.
Thanks, everybody. Thank you.